Okay, so this is going to be the second set of Chapter 7 videos. Like I said, Chapter 7 is usually spread out over 4 classes. We've dropped some material, so we're spreading out of like 3. It'd be like taking 3 classes. You will notice, again, I've listed a whole lot of resources. Chapter 7, again, I said this before, but it's like the crux of chemistry. It's why we want to understand chemistry and do chemistry. It's all about the reactions. So this is like the fundamental information you need to do to make reactions happen. So if you, in this section, don't like how I'm explaining something, you have tons of options. And I just put some in here. I do want to point out that this last one, this DeWitt one, I'm going to come back and actually do a little video showing this one because it helps understand what's actually going on in the water. All right, so can you mix any combinations of chemicals together in water and have them react? So what do you think? If you mix like some, I don't know, something in water, some salt in water. Let's say we got some salt in some water. And let's say we dissolve some sugar in some water. And then we mix them together. Does that mean that the sugar and the salt will always react with each other? So the answer would be no. I'm going to use 2 words that are not in this part of general chemistry. It's a preview of what's coming in general chemistry 2, and I'm just using the words so that you've seen them once for everyone moving on to Gen Chem 2. So there are 2 driving forces behind reactions. One is enthalpy, and enthalpy is energy. And everyone wants, I always talk about energy in terms of money. This is like how much, money that each compound has to share with someone else or to take from someone else in a way. You want to have extra energy at the end. You don't want to give out so much energy that you're having to borrow from someone else. So the idea is that it's usually very good when your energy is negative. Usually you want this to be negative. You can make things happen though with positive energy too, but that's one factor. There's this other factor. Entropy is called disorder. And I call this everyone wants to party. Basically, it goes with that idea that the universe is heading towards disorder. Anytime you set up a reaction that will make more disorder, then it's really a good thing for the reaction. So why do we care? Why are we using those 2 words? So those are the 2 basic things that you'll learn about in Gen Chem 2. And by the way, you want positive disorder. You want the disorder to be happening. But again, you won't be tested on that. I'm just giving you background here. In Gen Chem 1, we're going to talk about driving forces on the next page. So that's just a little preview. You have 2 driving forces, but there's some evidences of these driving forces existing. So just hang there for a second. I'm going to refer to it again. So terminology. Most general chemistry reactions have the solvent water. That's because water is easy to work with, and things that dissolve in water are often a lot safer. And you don't have to worry as much about things catching on fire or just other details. You get into organic chemistry, you will find that you have a solvent that is not water a lot of the time. A word that is going to come up again and again is this word precipitate. Now, in the weather, we talk about precipitate, and this is one case where actual terminology does not at all match with what you may be used to hearing, precipitate, water. Oh, there's precipitate. We have a lot of precipitate outside. It's not that. It's not water. What precipitate means is that you have solid particles. I'm not talking water. I'm talking like little clumps of solid. That's what a precipitate is in chemistry. So you want to have that in your head. You want to rearrange those words a little bit in the perspective of chemistry. If you have a solid sitting at the bottom of your water, that's because it's insoluble, meaning it won't dissolve. That's why it's sitting there. Like if you stir it, it's still going to sit there. That solid particle is insoluble in the water. So because it's a solid, we use the S to represent things. So S represents solid. It also represents the word insoluble. Just sitting at the bottom. It's like sand in water, insoluble. The solid on the bottom, the sand, that's your solid particle, and you would use an S to represent it. So what is insoluble? It is something that does not dissolve. And again, this is going to be solvent dependent, right? So we're talking about water. So for now, It's something that does not dissolve in water, but remember, this is also used in a larger context. So in organic chemistry, things can be insoluble in whatever solvent you're talking about. It could be insoluble in, I don't know, alcohol, or insoluble in ethyl acetate, ether, those kinds of things. All right, so here's where people get confused. What is a soluble solid? Okay, so this little pairing of words here, this is a weird pairing because the word soluble means that it is dissolve. So soluble is a dissolved solid. But I don't like to use the word solid, but Newton does use it, and that's why I've included it. So the reason I get a little antsy about using the word dissolved solid is because when something ionic dissolves in water, it breaks apart into its positive and negative charges. And it's actually super important that it does this. So here's a picture. I'm going to have my water right here. And this is the part where that video, DeWitt's video, is very, very helpful. So here's our water. And if I put NaCl in the water, so here's my NaCl. When I put it in the water, if I put a whole lot in, and it's like, remember we use that word saturated. So if it's saturated and I have way too much in, then the pile on the bottom is NaCl. But you know, NaCl does dissolve in water. So it also, the part that's dissolved when it goes into the water, Na pluses and Cl minuses. And just to take things slightly deeper, you might say, well, why aren't they attracted to each other? Okay, so they kind of are, but chapter 4, I'm going to zoom in really good in here. In chapter 4, we talked about water. So here's our water molecule. And we talked about how the water had a positive and a negative side. So this is the negative side of the water, and this is the positive side of the water. So guess what happens? The water has a strong enough dipole that it keeps the sodium attracted. So it's not saying that there isn't some attraction, but it's saying that the dipole that the water's making is strong enough to keep those two guys away from each other. And again, once I get to the point that there's so many of those NaCls in the water that it's saturated, meaning the water won't break apart any more of them, then it's just going to go to the bottom sitting as an NaCl. And this is something that would be repeated, but this might even be turned upside down in that case. There are some solids that water can't keep apart, some ions that water can't keep apart because they're too strongly attracted to each other. And in that case, every ion falls to the bottom, reattaches itself back together, and will not dissolve. So NaCl is soluble, and this is how something looks when it's soluble. So this is how it looks when it's soluble. And this is how something looks when it's insoluble. The letters we use are an S representing solid and an AQ representing soluble. Can't let yourself get those two things confused. S for solid, not soluble. AQ. AQ means that it's soluble in water. It also means one other thing too when you're talking about acids, which we'll talk about when we get to the acids. Alrighty, so you kind of see the difference between soluble and insoluble. A little Newton comment in there. The reason I don't like using the word dissolved solid is that once it's dissolved, it's not a solid anymore, it's ions, right? So, but Newton likes to use the word dissolved solid. So we'll just say that what this means is that the solid has split into ions. A little note, what is a gas? You know what it is. It's something that's in the gas phase. But the letter that we use for this is a G when it's a gas. Are they soluble in water? Well, think about carbon dioxide. Think about Cokes, if you call them pops. Think of those. There is a certain amount of solubility of some gases in water. So sometimes it depends, again, on the liquid and on the gas. But sometimes people don't think about that. As a note, what happens if you have a sealed container, and you're doing a reaction that produces so much gas that it won't dissolve in the water anymore. Yeah, it's going to break the container. Pop the lid off, whatever. It's going to, that gas that's being produced, it will escape. Gases are very strong. Is this an issue when you make a solid? Not usually, because solids don't take up as much space as gases, and because a lot of times solids are more soluble than the gas, but not usually because it's a small space. You still need to always be aware of doing any reaction under a sealed container is not a good idea, because you can produce gas, you could produce heat. It's a really bad idea. So don't close up your containers when you're doing reactions.